Strategic submarines still receive launch orders via radio waves at 76 Hz, a frequency so low that one wavelength spans 4,000 kilometers. 60 years of technological progress have not changed this. The problem is not engineering, it is physics. The infrastructure that nations built to work around it is as extreme as the weapons it controls. In 1968, Navy engineers set out to solve a problem that had stumped generations: how to reach submarines hidden far below the ocean's surface. Their answer was Project Sanguine, a plan that called for turning the ground itself into a transmitter. In the forests of northern Wisconsin, they buried more than 70 kilometers of copper wire in trenches carved through ancient rock, creating a vast mesh powered by 2 megawatts of alternating current. This ground plane antenna would send a 76 Hz signal, its wavelength nearly 4,000 kilometers, deep into the Earth, slipping beneath the sea to find submarines no other radio could touch. Early tests at Clam Lake proved extremely low frequency waves could travel through the ground and into the ocean, but building a working system was another challenge. Years of environmental studies and political debate followed. By 1979, the Navy received approval to construct full-scale sites at Clam Lake, Wisconsin, and Republic, Michigan. Each required nearly 120 kilometers of copper cable, arranged in loops to maximize contact with the Earth, and demanded 2 megawatts of power, running day and night. By October 1989, the system was operational. Now the United States could send a signal to any submerged ballistic missile submarine anywhere in the world. The achievement rested on buried copper, constant electricity, and the stubborn logic of low-frequency radio. In 1990, the Soviet Union launched the ZEVS transmitter near the Kola Peninsula, matching the American ELF system with its own vast antenna network. ZEVS operates at 82 Hz, stretching across more than 100 square kilometers of remote tundra. While the US decommissioned its ELF sites in 2004, ZEVS remains active, serving as Russia's main alert channel for ballistic missile submarines beneath the Arctic. Its continued operation reflects a Cold War consensus. ELF waves, with their ability to slip through seawater and ice, remain unmatched for reaching submerged vessels. Other countries face the same challenge and turn to the sky. The US Navy's TACAMO program, born in the late 1960s, began with the EC-130Q and evolved into the E-6B Mercury by 1991. These aircraft trail an 8-kilometer wire, broadcasting VLF signals at 24 kHz. From high above, a single E-6B can reach submarines far beyond the horizon, even if ground stations are lost. The trailing wire design, both simple and massive, is dictated by the physics of low-frequency transmission. Future plans for the E-130J, expected in 2027, will keep this architecture, pairing a 26,000-foot antenna with updated digital systems. Across Russia, America, India, and China, the same principle holds. Low-frequency radio remains the backbone of nuclear command, shaped not by preference but by the laws of nature. Seawater is an unyielding barrier for radio. Its conductivity, about 4 Siemens per meter, acts like a wall, swallowing most electromagnetic waves within a few meters. The deeper a submarine goes, the more complete the silence becomes. Only the lowest frequencies stand a chance. At 76 Hz, the wavelength stretches nearly 4,000 kilometers, about the distance from New York to Berlin. This is the scale of the old ELF system of the US Navy, and the reason the Soviet ZEV station on the Kola Peninsula settled on 82 Hz. The physics is blunt: the lower the frequency, the deeper the signal can reach. The so-called skin depth, calculated by a simple square root formula, tells how far a wave's energy will survive before it fades to a third of its surface strength. For ELF, that means more than 100 meters in cold, low-salinity water, enough to reach a ballistic missile submarine on patrol, even beneath Arctic ice. In typical ocean water, the practical skin depth is closer to 30 or 40 meters, but the magnetic field spreads wide enough to be picked up by sensitive induction coils on a submarine's hull, even at greater depths. Jump up to VLF, 24 kHz, the frequency used by TACAMO aircraft and most shore stations, and the story changes. The wavelength shrinks to about 12 kilometers, and the skin depth collapses to just a few meters. Submarines must rise to within 15 or 20 meters of the surface to catch the signal. Anything higher in frequency is lost almost instantly, absorbed by the ocean's salt ions. This is why satellites and digital networks, no matter how advanced, cannot reach a sub at launch depth. The laws of physics demand antennas measured in kilometers and a patience for data rates that crawl, 1 bit per minute at best. Dr. Elena Petrova of the Naval Research Laboratory says that if you want a signal to reach 300 meters underwater, you must go below 100 Hertz. Higher frequencies simply die out after a few meters. The result is a communication system that looks primitive by modern standards, yet remains the only option for silent, survivable command. The promise of global reach vanishes once the question turns to bandwidth. At 76 Hz, the United States Navy's old extremely low frequency system could transmit no more than 1 bit per minute. This is not a technical oversight, but a direct result of the physics. The lower the frequency, the longer each cycle, and the more time required to distinguish a deliberate signal from background noise. Engineers faced a stark trade-off: either penetrate the ocean's depth, or send any meaningful volume of information, but never both. To ensure the signal is real, each bit must be integrated over many cycles, often for 60 seconds or more. The result is a data channel so narrow that a 3-letter code, enough for 17,576 unique combinations, takes 15 minutes to send. This is the practical ceiling for an extremely low-frequency message. The protocol is designed around this constraint. Each submarine receives a tiny, pre-arranged prompt, a bell ringer, alerting the crew that something urgent is coming. There is no room for a full launch order, coordinates, or even a complete sentence. The operational consequences are unavoidable. A submarine on patrol, hundreds of meters below the surface, can wait hours or days for a signal. But when the extremely low-frequency tone finally arrives, all it carries is the barest nudge: rise to communications depth and listen for more. The rest of the story, the detailed order and its authentication codes, must be delivered by very low-frequency transmissions or satellite, and only after the submarine exposes itself to the surface. The most advanced weapons platform on Earth begins its chain of command with a message that crawls through the ocean at the speed of a telegraph. A submarine on patrol receives its bell ringer code deep below the surface, but that signal is only the start. The next step is a calculated risk. The crew must bring the boat to within 20 meters of the surface, close enough for VLF reception, but also close enough to be spotted by sonar, radar, or a passing aircraft. Every ascent is a trade-off between the need for orders and the need for stealth. Procedures are drilled so that the maneuver takes minutes, but in those minutes the submarine's acoustic and electromagnetic signature rises sharply. For the crew, this is not a theoretical risk. It is a moment of vulnerability, repeated every time a detailed message is needed. Maintaining the infrastructure for these fleeting signals comes at a real cost. In its final decade, the US Navy spent about $25 million each year just to keep the ELF network running, paying for electricity, repairs, and the constant monitoring required by legal settlements. That cost was not only financial. In northern Wisconsin and Michigan, local residents and activists sustained a protest movement for more than 30 years, challenging the presence of high-power transmitters in their communities. Lawsuits, environmental reviews, and public hearings became as much a part of Project ELF as the copper buried in the ground. Yet despite decades of opposition and the steady march of digital technology, navies around the world continue to invest in these low-frequency systems, accepting the operational exposure and the controversy as the price of a message that can reach a submarine anywhere at depth. Low-frequency radio remains the only way to reach a submerged ballistic missile submarine. India's INS Kattabomman, active since 2014, sends VLF signals from Tamil Nadu to Arihant-class boats, cutting through the Indian Ocean. China's Datong station, upgraded in 2021, links to Jin-class submarines, keeping VLF coverage across the Pacific. Russia's ZEVS ELF transmitter still operates near the Kola Peninsula, a reminder that seawater's physics set the rules. The United States will carry this forward. Columbia-class submarines, due in 2031, will use VLF relayed by Takamo aircraft. The E-130J, arriving 2027, keeps the trailing wire 26,000 feet, now with tougher encryption and avionics. No satellite or quantum link can reach a boat at depth. Security layers sit atop this. Permissive action links, mechanical electrical locks that require a sealed code, a two-person check, and a physical key stand between any signal and a launch. The world's most advanced weapons still wait for the slowest signal, not a mythic instant command. Submarines carrying nuclear missiles still wait for orders at 76 Hertz, through antennas that stretch for miles, or because seawater swallows modern signals. The irony is inescapable. Cold War physics, not digital innovation, still decides what survives beneath the waves. Deterrence remains hostage to the laws of nature.